In late 2025, a team of astronomers published a paper that said something strange. They claimed the universe is not speeding up, that the Nobel Prize-winning discovery of cosmic acceleration might be wrong, the result of a measurement bias nobody had properly accounted for. In June 2026, a different team published their answer. They went through the math, re-examined the data, and concluded, no, the universe is still accelerating. The evidence holds. But the way they settled this argument reveals something most people never think about. How do you measure the speed of the entire universe when you cannot step outside it and watch? You cannot point a speedometer at empty space. Space does not move through anything. It stretches. And the only way to detect that stretching is to find objects so far away that the light reaching us has been traveling for billions of years. That light carries a record of how much space expanded while it was in transit. The tool astronomers use for this is a specific kind of exploding star. A type A supernova happens when a white dwarf, the dense remnant of a dead star, reaches a critical condition and detonates. One route is a white dwarf pulling material from a companion star. Another is two white dwarfs merging. Either way, the explosion can outshine an entire galaxy for weeks. Because these explosions happen in a narrow physical range, their peak brightness is predictable. Not identical. Astronomers still correct for the details, how quickly the supernova fades, its color, properties of the host galaxy, and calibration data. After those corrections, they get a reliable brightness. Compare that corrected brightness with how bright the supernova appears from Earth, and you get its distance. Now combine the two measurements. Redshift tells you how much the universe expanded while the supernova's light was traveling. Corrected brightness tells you how far away it is. Plot many supernovae on a graph, distance against redshift, and the shape of that curve reveals the expansion history of the universe. In 1998, two independent teams measured this. The High-Z Supernova Search Team and the Supernova Cosmology Project both found the same thing. Distant supernovae were dimmer than expected. They were farther away than they should be in a universe whose expansion was only slowing under gravity. The conclusion? The expansion of the universe started accelerating roughly 5 billion years ago. Something was pushing space apart faster than gravity could pull it back together. That something got the name dark energy. In 2011, the lead researchers won the Nobel Prize. That picture held for more than 2 decades. Then, in late 2025, a team from Yonsei University in South Korea challenged the foundation. Their argument was that the age of the star that explodes affects the supernova brightness even after standard corrections. Younger progenitor stars produce slightly different explosions than older ones. And because distant supernovae come from younger cosmic times, this age difference could create a systematic tilt in the data. In their corrected version of the Hubble diagram, acceleration was no longer required. The universe might even be decelerating right now. The claim got attention for an obvious reason. A Nobel-winning result might be wrong. But in June 2026, Phil Wiseman and colleagues at the University of Southampton published a direct response in monthly notices of the Royal Astronomical Society. They identified 2 concrete problems with the Yonsei analysis. First, the original study treated the average age of stars in the host galaxy as a stand-in for the age of the specific star that exploded. Those are different things. A galaxy's average stellar age reflects its whole history. The white dwarf that detonated could be much older or younger than that average. Second, the Yonsei analysis left out a standard correction that supernova cosmologists already apply, a correction for the total stellar mass of the host galaxy. When Wiseman's team included both fixes, the acceleration evidence came back. The Hubble diagram still bends the way it did in 1998. So the supernova evidence survives. But a separate question is being tested right now by a completely different instrument. The Dark Energy Spectroscopic Instrument, DESI, sits on a 4-meter telescope at Kitt Peak, Arizona. It uses 5,000 tiny robotic fiber optic positioners to capture the light of galaxies and quasars across the sky, measuring their redshifts one by one. By April 2026, DESI had mapped more than 47 million galaxies and quasars, building the largest three-dimensional map of the universe ever made. DESI does not use exploding stars. It uses a fossil pattern from the early universe. About 370,000 years after the Big Bang, pressure waves rippling through the hot plasma froze in place when the universe cooled enough for atoms to form. Those waves left a preferred separation between clumps of matter, roughly 490 million light-years in today's distances. That separation shows up as a slight excess of galaxy pairs at that distance apart. Astronomers call it the Baryon Acoustic Oscillation Scale, and it works as a cosmic ruler. Measure that ruler at different cosmic ages, and you can trace how the universe expanded over time without relying on supernova brightness at all. DESI's early results, from its first 3 years of data, are broadly consistent with the standard model of dark energy. A cosmological constant, the same push at every point in space and time. But when DESI data are combined with other measurements, including the cosmic microwave background, weak gravitational lensing, and supernova compilations, there are hints. Mild statistical tension suggests dark energy might not be constant. It might be changing over time. The evidence is suggestive, not conclusive, and below the threshold physicists require for a discovery claim. DESI's full 5-year analysis is expected in 2027. That distinction is easy to lose. The June 2026 rebuttal says the supernova evidence for acceleration is solid. The expansion history curve still bends upward. DESI asks another question. Is the thing causing that bend constant, or is it changing strength? Both can be true. The universe can be accelerating while dark energy is evolving. These are different measurements, answering different parts of the same puzzle. The answer shapes the future of the universe. If dark energy is a true cosmological constant, the same strength forever, the universe keeps accelerating. Galaxies beyond our local group recede faster and faster. The observable universe slowly empties. In the far future, distant galaxies fade from view entirely. If dark energy weakens over time, gravity could eventually regain the upper hand. Expansion could slow, stop, or even reverse. And if dark energy strengthens, the acceleration worsens until the fabric of space tears apart, a scenario physicists call the Big Rip. Right now, the data favor continued acceleration, with possible hints of change. Not enough to pick a fate, but enough to know the question is genuinely open. So here is where things stand. The universe is still accelerating. The June 2026 rebuttal says the supernova evidence that won a Nobel Prize in 2011 survives this specific challenge. The challenge was real science, not a fringe claim, but it depended on assumptions the new analysis says do not hold. Meanwhile, DESI has built the most detailed three-dimensional map of the cosmos ever assembled, and its full analysis could sharpen or shift the picture in 2027. We know the universe is speeding up. What we still do not know is whether the force behind that acceleration is a permanent feature of space, or something that changes. And that question may decide how the universe ends.